Network Time Protocol is a networking protocol for clock synchronization between computer systems over packet-switched, variable latency data networks. In operation since before 1985, NTP is one of the oldest Internet protocols in current use. NTP was originally designed by David L. Mills of the University of Delaware, who still oversees its development. NTP is intended to synchronize all participating computers to within a few milliseconds of coordinated universal time. It uses a modified version of Marzullo's algorithm to select accurate time servers and is designed to mitigate the effects of variable network latency. NTP can usually maintain time to within tens of milliseconds over the public Internet, and can achieve better than 1 millisecond accuracy in local area networks under ideal conditions. Asymmetric routes and network congestion can cause errors of 100 milliseconds or more. The protocol is usually described in terms of a client-server model, but can as easily be used in peer-to-peer relationships where both peers consider the other to be a potential time source. Implementations send and receive timestamps using the user datagram protocol on port number 123. They can also use broadcasting or multicasting, where clients passively listen to time updates after an initial round-trip calibrating exchange. NTP supplies a warning of any impending leap-second adjustment, but no information about local time zones or daylight saving time is transmitted. The current protocol is version 4, which is a proposed standard as documented in RFC 5905. It is backward compatible with version 3, specified in RFC 1305. History. In 1979, network time synchronization technology was used in what was possibly the first public demonstration of Internet services running over a transatlantic satellite network, at the National Computer Conference in New York. The technology was later described in the 1981 Internet Engineering Note 173 and a public protocol was developed from it that was documented in RFC 778. The technology was first deployed in a local network as part of the Hello routing protocol and implemented in the fuzzball, an experimental operating system used in network prototyping, where it ran for many years. Other related network tools were available both then and now. They include the daytime and time protocols for recording the time of events, as well as the ICMP timestamp and IP timestamp option. More complete synchronization systems, although lacking NTP's data analysis and clock disciplining algorithms, include the Unix daemon timed, which uses an election algorithm to appoint a server for all the clients, and the digital time synchronization service, which uses a hierarchy of servers similar to the NTP stratum model. In 1985, NTP v0 was implemented in both fuzzball and Unix, and the NTP packet header and round-trip delay and offset calculations, which have persisted into NTP v4, were documented in RFC 958. Despite the relatively slow computers and networks available at the time, accuracy of better than 100 milliseconds was usually obtained on Atlantic-spanning links, with accuracy of tens of milliseconds on Ethernet networks. In 1988, a much more complete specification of the NTP v1 protocol, with associated algorithms, was published in RFC 1059. It drew on the experimental results in clock filter algorithm documented in RFC 956 and was the first version to describe the client-server and peer-to-peer modes. In 1991, the NTP v1 architecture, protocol and algorithms were brought to the attention of a wider engineering audience with the publication of an article by David L. Mills in the IEEE Transactions on Communications. In 1989, RFC 1119 was published defining NTP v2 by means of a state machine, with pseudocode to describe its operation. It introduced a management protocol and cryptographic authentication scheme which have both survived into NTP v4. The design of NTP was criticized for lacking formal correctness principles by the DTSS community. Their alternative design included Marzullo's algorithm, a modified version of which was promptly added to NTP. The bulk of the algorithms from this era have also largely survived into NTP v4. In 1992, RFC 1305 defined NTP v3. The RFC included an analysis of all sources of error, from the reference clock down to the final client, which enabled the calculation of a metric that helps choose the best server where several candidates appear to disagree. Broadcast mode was introduced. In subsequent years, as new features were added and algorithm improvements were made, it became apparent that a new protocol version was required. In 2010, RFC 5905 was published containing a proposed specification for NTP v4, but the protocol has significantly moved on since then, and as of 2014, an updated RFC has yet to be published. Following the retirement of Mills from the University of Delaware, the reference implementation is currently maintained as an open-source project led by Holland Sten. Clock Strata. NTP uses a hierarchical, semi-layered system of time sources. Each level of this hierarchy is termed of stratum, and is assigned a number starting with 0 at the top. A server synchronized to a stratum n server will be running at stratum n+1. The number represents the distance from the reference clock and is used to prevent cyclical dependencies in the hierarchy. Stratum is not always an indication of quality or reliability. It is common to find stratum 3 time sources that are higher quality than other stratum 2 time sources. Telecommunication systems use a different definition for clock strata. A brief description of strata 0, 1, 2 and 3 is provided below. Stratum 0. These are high-precision timekeeping devices such as atomic clocks, GPS clocks or other radio clocks. They generate a very accurate pulse-per-second signal that triggers an interrupt and timestamp on a connected computer. Stratum 0 devices are also known as reference clocks. Stratum 1. These are computers whose system clocks are synchronized to within a few microseconds of their attached Stratum 0 devices. Stratum 1 servers may pair with other Stratum 1 servers for sanity checking and backup. They are also referred to as primary time servers. Stratum 2. These are computers that are synchronized over a network to Stratum 1 servers. Often a Stratum 2 computer will query several Stratum 1 servers. Stratum 2 computers may also pair with other Stratum 2 computers to provide more stable and robust time for all devices in the peer group. Stratum 3. These are computers that are synchronized to Stratum 2 servers. They employ exactly the same algorithms for peering and data sampling as Stratum 2, and can themselves act as servers for Stratum 4 computers, and so on. The upper limit for Stratum is 15. Stratum 16 is used to indicate that a device is unsynchronized. The NTP algorithms on each computer interact to construct a Bellman-Ford shortest path spanning tree. To minimize the accumulated round-trip delay to the Stratum 1 servers for all the clients. Timestamps. The 64-bit timestamps used by NTP consist of a 32-bit part for seconds and a 32-bit part for fractional second, giving a timescale that rolls over every 232 seconds and a theoretical resolution of 2-32 seconds. NTP uses an epoch of January 1, 1900, so the first rollover will be in 2036. Future versions of NTP may extend the time representation to 128 bits, 64 bits for the second and 64 bits for the fractional second. The current NTP v4 format has support for era number and era offset, that when used properly should aid fixing date rollover issues. According to Mills, The 64-bit value for the fraction is enough to resolve the amount of time it takes a photon to pass an electron at the speed of light. The 64-bit second value is enough to provide unambiguous time representation until the universe goes dim. Clock synchronization algorithm. A typical NTP client will regularly poll 3 or more servers on diverse networks. To synchronize its clock, the client must compute a time offset and round-trip delay. Time offset theta is defined by, and the round-trip delay delta by, where T0 is the client's timestamp of the request packet transmission. T1 is the server's timestamp of the request packet reception. T2 is the server's timestamp of the response packet transmission, and T3 is the client's timestamp of the response packet reception. The values for theta and delta are passed through filters and subjected to statistical analysis. Outliers are discarded and an estimate of time offset is derived from the best 3 remaining candidates. The clock frequency is then adjusted to reduce the offset gradually, creating a feedback loop. The synchronization is correct when both the incoming and outgoing routes between the client and the server have symmetrical nominal delay. If the routes do not have a common nominal delay, there will be a systematic bias of half the difference between the forward and backward travel times. Software implementations. Reference implementation. The NTP reference implementation, along with the protocol, has been continuously developed for over 20 years. Backwards compatibility has been maintained as new features have been added. It contains several sensitive algorithms, especially to discipline the clock, that can misbehave when synchronized to servers that use different algorithms. The software has been ported to almost every computing platform, including personal computers. It runs as a daemon called NTPD under Unix or as a service under Windows. Reference clocks are supported and their offsets are filtered and analyzed in the same way as remote servers, although they are usually polled more frequently. SNTP, a less complex implementation of NTP, using the same protocol but without requiring the storage of state over extended periods of time, is known as the Simple Network Time Protocol. It is used in some embedded devices and in applications where high accuracy timing is not required. Windows Time Service. All Microsoft Windows versions since Windows 2000 include the Windows Time Service, which has the ability to synchronize the computer clock to an NTP server. The W32 time service was originally implemented for the purpose of the Kerberos version 5 authentication protocol, which required time to be within 5 minutes of the correct value to prevent replay attacks. The version in Windows 2000 and Windows XP only implements simple NTP, and violates several aspects of the NTP version 3 standard. Beginning with Windows Server 2003 and Windows Vista, a compliant implementation of full NTP is included. Microsoft says that the W32 time service cannot reliably maintain sync time to the range of 1 to 2 seconds. If higher accuracy is desired, Microsoft recommends using a different NTP implementation. N-Timed. A new NTP client, N-Timed, was started by Paul Henningkamp in 2014. The new implementation is sponsored by the Linux Foundation as a replacement for the reference implementation, as it was determined to be easier to write a new implementation from scratch than to fix the existing issues with the large existing code base. As of June 2015, no official release was done yet, but N-Timed can synchronize clocks reliably. N-Timed works under Debian GNU, Linux and FreeBSD, but remains to be ported to Windows and Mac OS. Leap seconds. On the day of a leap second event, NTPD receives notification from either a configuration file, an attached reference clock, or a remote server. Because of the requirement that time must appear to be monotonically increasing, a leap second is inserted with the sequence 235959235960000000. Although the clock is actually halted during the event, any processes that query the system time cause it to increase by a tiny amount, preserving the order of events. If it should ever become necessary, a leap second would be deleted with the sequence 2359580000, skipping 235959. Security concerns. Several security concerns arose in late 2014. Previously, researchers became aware that NTP servers can be susceptible to man-in-the-middle attacks unless packets are cryptographically signed for authentication. The computational overhead involved can make this impractical on busy servers, particularly during denial-of-service attacks. Some of the services impacted by fake NTP messages identified are TLS, DNSSEC, various caching schemes, BGP, Bitcoin, and a number of persistent login schemes. Only a few other security problems have been identified in the reference implementation of the NTP codebase in its 25-plus year history. But the ones that have appeared recently are cause for significant concern. The protocol has been undergoing revision and review over its entire history. As of January 2011, there are no security revisions in the NTP specification and no reports at CERT. The current codebase for the reference implementation has been undergoing security audits from several sources for several years now, and there are no known high-risk vulnerabilities in the current release software. Several NTP server misuse and abuse practices exist which cause damage or degradation to a network time protocol server. NTP has been used in distributed denial-of-service attacks. A small query is sent to an NTP server with the return address spoofed to be the target address. Similar to the DNS amplification attack, the server responds with a much larger reply that allows an attacker to substantially increase the amount of data being sent to the target. To avoid participating in an attack, servers can be configured to ignore external queries, or they can be upgraded to version 4.2.7p26 or later. A stack-based buffer overflow exploit was discovered and a patch is available as of December 19, 2014. This includes all NTP version 4 releases before version 4.2.8. Apple was concerned enough that it used its auto-update capability for the first time, though only for recent versions of OS X. In the case of version 10.6.8, there are manual fixes for the server version, and normal client users can just turn off automatic time updating in system preferences for date and time. Researchers believe that the protocol design is excellent and that the flaws are appearing in implementations of the protocol. Some errors are basic, such as a missing return statement in a routine. That can lead to unlimited access to systems that are running some versions of NTP in the root daemon. Systems that do not use the root daemon, such as BSD, are not subject to this flaw.